This lesson deals with a Fourier series. You can find these notes in the ECE202 ebook in Chapter 13, starting on page 1. Given a function f of t which is periodic and has a period t0, then f of t can be written as the following summation. a0 plus the sum from n equals 1 to infinity of the quantity a sub n cosine of 2 pi n f naught t plus b sub n times the sine of the quantity 2 pi n f naught t, where a0 is the DC component or average value of f of t, and a sub n and b sub n are the Fourier coefficients. a0 is 1 over the period, integral from minus t0 over 2 to t0 over 2 of f of t dt. A sub n is 2 over t0, the integral from minus t0 over 2 to t0 over 2 of f of t times the cosine of 2 pi nt divided by t0 dt. And b sub n is 2 over t0, integral from minus t0 over 2 to t0 over 2 of f of t times the sine of 2 pi nt divided by t0 dt. Now why would that be true? Let's first find the term a0. To do that, let's integrate both sides of the equation of f of t. We'll take the left-hand side of the equation and integrate from minus t0 over 2 to t0 over 2, really over one period, dt. I'll do the same thing to the right-hand side of the equation. The first term is a0, but that's just a constant, so we can pull it out in front, and take the integral from minus t0 over 2 to t0 over 2 of just 1 dt. And then we'll take the integral of the sum, but the integral of the sum is the sum of the integrals, so we can bring that integral inside. Coefficients are just constants, so we're going to pull that out. And I've got the integral from minus t0 over 2 to t0 over 2 of the cosine of 2 pi n f naught t dt, plus pull out the b sub n, and then the integral from minus t0 over 2 to t0 over 2 of the sine of 2 pi n f naught t dt. The integral of 1 dt is just t, evaluated at the upper limit minus the lower limit. That's this term minus this term. And the integral of the cosine function over a period is just equal to 0. It's above 0 as much as it's below 0 in one period, even if there are multiple cycles per period. The same is true for the sine wave. And so now we can solve for a0. So then a0 is equal to, divide on the other side of the equation, the sum of these two is just equal to 2t0 over 2, or just t0. So 1 over t0, the integral from minus t0 over 2 to t0 over 2 of f of t dt. Next, to find the term a sub n, let's multiply both sides of f of t by the cosine of 2 pi m f naught t and integrate over a period. The left-hand side of the equation had f of t. We're going to multiply that by our cosine dt and then integrate from minus t0 over 2 to t0 over 2. Now on the right-hand side of the equation, do the same thing. Our term a0 is just a constant, so we're going to pull that out in front, and I've got that integral over a period of the cosine of 2 pi m f naught t dt. Plus our summation from n equals 1 to infinity, and I'll bring the integral inside. Again, a sub n is just a constant, so we'll pull that out. We've got the integral over a period of the cosine of 2 pi m f naught t times the cosine of 2 pi n f naught t dt. Likewise for the second term, I'll pull out the b sub n, multiplying through by the cosine of 2 pi m f naught t, and the other term that was there was the sine of 2 pi n f naught t dt. I've got a product of cosine, cosine, and cosine sine, so let's pull some trig identities up. And recall the following. The sine times the cosine is 1/2 the sine of the difference plus 1/2 sine of the sum. Cosine cosine is 1/2 the cosine of the difference plus half the cosine of the sum. Cosine sine is minus 1/2 the sine of the difference plus 1/2 sine of the sum. And then sine sine is 1/2 the cosine of the difference minus 1/2 the cosine of the sum. Let's use these above. Here's my left-hand side of the equation. On my right-hand side of the equation, I've got a0 times this integral. And then inside the summation, I have this product of cosine. So we just take this cosine cosine, then we're going to use that identity, which is 1/2 the cosine of the difference plus 1/2 the cosine of the sum. The difference would be m minus n, and then m plus n is the sum. The second term has cosine sine, so go grab that one. Here's the cosine sine, so it's minus 1/2 of the sine of the difference plus 1/2 the sine of the sum. And that's shown below. Here's my minus 1/2, here's the difference, and then here's the sum. Now let's let m equal n. So on the right-hand side of the equation, I have a0 times the integral over a period of the cosine of 2 pi m equals n f naught t, but the integral of a cosine over a period is just equal to 0. In other words, the area above 0 is the same as the area below 0 in one period. Although this term here, I've got m equal to n, so I've got the cosine of 0, but that's equal to 1. Here, when m equals n, I've got the cosine of 2 pi times 2n f naught t naught, and again, that's the integral of a cosine over a period, which is going to be equal to 0. Here I have the sine of 0, but the sine of 0 is 0. And lastly, I've got the sine of 2n over here, and the integral of a sine over a period is equal to 0. All the integrals are equal to 0 except this one where I have the cosine of 0. Now what's the value of that integral? Well, the cosine of 0 is 1. Pull that out in front. So I got the integral of 1 dt. That's just going to be equal to t, upper limit minus the lower limit. I get t0 over 2 twice, or just t0. So here's my left-hand side of the equation. My right-hand side of the equation, all I've got is then a sub n over 2, and then times t0. I can solve for a sub n. Bring the t0 on this side of the equation by dividing by it, and then cross-multiply by 2, and that's my value for a sub n. Next, to find b sub n, let's multiply both sides of the equation by now the sine of 2 pi m f naught t, and then integrate over a period. The left-hand side of the equation was this f of t, and now we're going to multiply by the sine, dt, integrate over a period. On the right-hand side, we have a0 as the first term. It's going to pull that out because it's not a function of time, and then we've got this integral over a period of the sine of 2 pi m f naught t dt. Then our summation from n equals 1 to infinity. The a sub n term will pull out as a constant, and I've got the sine now multiplied by the cosine on that right-hand side of the equation, and I've got the sine of 2 pi m, and here I've got the cosine of 2 pi n. The second term, pull out the b sub n, and I've got the sine of 2 pi m, and then the sine of 2 pi n. So here I've got sine times cosine, and then sine times sine. So let's again use those trig identities on the previous page to simplify the results. Here's my left-hand side of the equation, my right-hand side of the equation, and then I've got this term here of sine times cosine. So from the previous page, the identity is 1/2 the sine of the difference plus 1/2 the sine of the sum. And then the second term is sine times sine, and that's the last of the 4 trig identities. And that's going to be 1/2 the cosine of the difference minus 1/2 the cosine of the sum. And I'm pulling out that 1/2 in front. Again, if I let m equals n, something interesting happens. This becomes the sine of 0, which is just equal to 0. Here I've got the sine of 2n. The integral of the sine over a period is just equal to 0. Here I've got the difference, so I get 0, and so I get the cosine of 0, which is just equal to 1. And then lastly, I have this term, which is 2 pi times twice n. And again, it's over a period, so this integral will be equal to 0. So all the integrals are equal to 0, except this one here, which is the cosine of 0. Then the integral of 1 dt is just equal to t, upper limit minus the lower limit, so twice t, 0 over 2, so we just get t0. Then we can put our results together. And we have the left-hand side of the equation, and then equal to bn over 2, then times t0. And then we can solve for b sub n. Bring the 2 over here and divide by the t0, and that's our definition of b sub n. That proves our theorem, deriving the value of a0, a sub n, and b sub n. Just one footnote. In doing the Fourier series in this last theorem, we were doing a period from minus t0 over 2 to t0 over 2. But actually it can be any period. For example, you go from 0 to t0, from minus a quarter t0 to 3/4 t0. The reason for doing this is that by selectively picking where the period is going to be to and from, we can make the integration a lot easier. And this is the Fourier series.